All right, in this question, we were given a matrix X. Technically, it's called X tilde, and that little squiggle on top means its columns have been mean-centered, meaning they all have means of 0. But for the rest of this video, I'm just going to call that matrix X. We're told that X is a 20 by 3 matrix, so it has 3 columns and 20 rows, and it has a singular value decomposition U sigma V transpose. Additionally, we are told that the 3 columns of X have variances of 125, 20, and 5, and we were asked to find the minimum possible value of sigma 1, which is the largest singular value of X. Remember, this sigma matrix in the singular value decomposition, since X here has 3 columns, this matrix is going to be 20 by 3 as well. Remember, sigma and X have the same shape in the singular value decomposition. And the way that this is going to look is that we're going to have sigma 1 up here, 0, 0, 0, sigma 2, 0, 0, 0, sigma 3, and then just 17 rows of all zeros. That's what sigma is going to look like. And we're asked to find the minimum possible value that could appear in the top left entry of the sigma matrix. Now, what's going on here? Remember, there's a connection between singular values, that is the sigmas in this matrix, on the diagonal of this matrix, and the variances of something. But the connection between the sigmas and the variances relates the sigmas to the variances of the principal components, which are those new features we are creating by taking optimal linear combinations of our original features. The key idea here is that the variance of principal component J, that is, J could be 1, meaning our first new feature, that is the one feature that captures the most, the one new feature that captures the most variance in our data, or PC2 would be the next new feature after we've accounted for the variance in the direction of the first feature, and so on. The variance of principal component J is sigma J squared over the number of data points, which here is 20. Now, what is the actual value of sigma 1? I don't have enough information in this question to determine it, right? It would depend on what the actual numbers in the X matrix are. But remember, a principal component is just a linear combination of my original features. And so if I'm approaching this from a, what could the simplest first principal component be, given no other information about the data set, the naive or base case solution I could think of is, well, the best first principal component has got to be at least as good, if not better than, picking just one of the original columns of X that has the most variance, which in this case would be the first one, which has a variance of 125. Here's what I mean. V1, that is the eigenvector of xtx with the largest eigenvalue, is going to be some vector in R3. It's going to tell us how much to take of x's first column, how much to take of x's second column, and how much to take of x's third column to make that optimal linear combination that we will call principal component 1. Right? The real value of V1, I don't know what it's going to be. It could be like 1/9, 2/5, and 17. It wouldn't be exactly this because it needs to be a unit vector, and so length would need to be 1, but it would be something like this. It would be a linear combination of the original 3 columns of X. What I'm saying is, I don't actually have the information in X. What I do know are the variances of the 3 columns, and I know that if principal component 1 is designed to capture as much variance as it can, which it is, it's got to be at least as good as picking V1 to be 1, 0, 0, which is the way, with the information that I have, to make the variance of the first principal component maximized. And V1 being 1, 0, 0 just means selecting the first column of X, right? X times V1 is just X's first column, if I make V1 to be 1, 0, 0. And so my point is, the variance of the first principal component has to be greater than or equal to 125. And using that idea, I can find what the minimum possible value of sigma 1 should be. So the idea here is that the variance of principal component 1, which is sigma 1 squared over n, it has to be greater than or equal to 125. We've got to be able to do better than just saying pick the column with the most variance. Okay? The best direction in the data probably doesn't just use one column, but it's, some amount of all of the columns in my data set. So this expression must be true, and now this really just resolves to solving this inequality for the value of sigma 1 on the threshold. What is n here? N is 20. So now we get to do some math. I'm looking for where sigma 1 squared is greater than or equal to 125 times 20, which notice is equal to 250 times 10, so 2,500. And so what I can do is take the square root of both sides here. Let me repeat the current value of the inequality. If I take the square root of both sides, that will give me that sigma 1, which I know has to be non-negative, right? A singular value of a matrix is the square root of the eigenvalue of some other matrix. And so since this is the square root, it can't be negative. So we know that this is going to be non-negative, which is why this is a legal operation. Sigma 1 then has to be greater than or equal to 50, which is the square root of 2,500. So what is the minimum possible value of sigma 1, the first singular value of x? It is 50. Great.